Today.
Are they already posted on Blackboard?
I was just gonna see if I had to hit the post button. They should be posted.
I've just been curious, so I've been checking every
Oh.
day.
They were not posted. Okay. Come on. All right, now they are posted.
Maybe check the chapter 17 notes because it wasn't working for me. When I open it, it just says like the big X thing.
Yeah, well, I'll look.
Okay.
It should be going. So. Yeah, put your name on it there. Thank you. All right, let's get started. Just a couple of announcements. There's a lot of stuff going on. So coming up, and of course you may have already seen these flyers around campus, but you know that Tony Cremo has been setting up some lecture series, and so the next one features a chiropractic doctor, and so that's going to be next Friday. If you're interested, it's going to be 4 to 5 p.m. And I may offer some extra credit. That's what I'm kind of thinking, 5 extra points for attending. And it will be recorded and whatnot, so if you don't come in person and sign in, then you can just send me, a sentence or two about the talk or whatever. So that's on the radar. It is not yet. So the flyers are all around. I'll try to post it on Blackboard, but time is limited. And so there's also happening today, Chat with Randy. And so that's going to be, I think that starts at noon to 1. So I think it's downstairs, but there's free pizza. So you might want to check that out. You're president of the university? Yeah. Well, maybe you should go chat with Randy since you don't know who the president is. But yeah, it's good to chat with the president of your university to figure out where the heck, their head is and what they're thinking, and then you can advocate for your favorite campus. Other random opportunities. I don't know if you guys have heard about this in your other classes, but there's some Oregon wine research or something going on. So if you're interested, let me know. I'll try to post it on Blackboard, but I'm not making promises that I'll remember.
When is that research happening?
Let me look at the flyer again. Yeah, I think it was for the summer. So if you don't have an REU lined up, and this is just a reminder to, apply for an REU. It doesn't say, but I assume this is going on during the summer. That's annoying that you have to click the thingy. Obviously, I don't have my phone hooked up. And I thought there was one more opportunity. No, the research, or the chat with Randy is today, yeah. So pizza is today, free pizza today. The research, I think, is happening in the summer. And then there's also another local internship. Again, if you're interested, pester me, and don't wait for me to post it because I might forget. But Jackson County is doing some sort of tracking vector diseases. Apparently some mosquito was spotted in Jackson County or in Oregon or something. And so they're looking for people to help for that. I think that's in the summer. So the deadline is coming up, but local. So yeah, you could head to there, but like I said, just pester me and I can give you more information. I'll try to post these, but otherwise, right, sign up for an REU or something. So again, I'll just think of summer plans. And then on that note, or kind of in that similar vein of outreach, so a few of you have been talking to me about outreach, and so we're going to have a meeting. It's going to be in the HEC in the lab room this Friday at 11 a.m. And so I think I mainly have my volunteers set, but we could use a few hands, extra volunteers for especially Wednesday. So this is going out, getting ready to go out to the Boys and Girls Club. So we're just meeting to discuss and practice some of the experiments that we'll be doing. So if you're interested, even if you can't commit to the Boys and Girls Club thing right now, maybe you want to come by to see what's going on, because we do want to plan something for the summer too with the Boys and Girls Club. So lots of good opportunities there. So again, Friday at 11, this Friday, if you want to come, just find out more information, or if you're committed, then I've already emailed y'all and hopefully you'll be coming. But yeah, not too late to join. Okay, I think that's all the announcements. I did grade your midterm, but I'll talk about that later. All right, let's shift gears for a second. So we pretty much covered Chapter 17 on Tuesday. So if you weren't here in person, there's the cheat sheet notes mainly, which is like all the formulas you need to know. And so now let's shift gears and let's look back at our lab. So let's start with that. So this is our acid-base titration lab. And, you know, admittedly, again, with the curriculum, there's not a good place to put this lab because we don't touch acids and bases till like the very last few weeks. And then we don't want to be trying to shove this, you know, lab at the end. So that's why it's here. And so let's kind of go over the math, what's going on here. We'll go a little bit into the theory, but then, like I said, I'll just kind of show you how to do the math. We'll get into it later in lecture, but at least you'll know how to do your problems. And so just kind of a quick kind of what's going on. I'll put this as our kind of background. And so we may be familiar with a strong acid. And so a strong acid just means that it completely disassociates. And so all that's saying is, okay, well, let's say we have, right, 1 molar solution of hydrochloric acid, right? So then it's going to disassociate completely, and then you make, right, 1 mole of course, H+ ions, 1 mole of your chloride ions, and then we could plug in, right, our pH. And so this is just a formula for pH. And so pH is equal to the negative log of your concentration of your H+ ions, and this is molar concentration. So yay, right? So it's really easy for our strong acids and bases, right, that completely disassociate. So the first problem that we're going to encounter and that we're going to learn, right, and where all the math comes in, is that this is a weak acid, and it does not fully disassociate. And so now we'll write that. And now we'll say, okay, in our case, citric and many other organic acids is weak. And again, all this means it has nothing to do with how dangerous it is. We'll get into this again with our acid chapter. But it just means it does not fully dissociate. And okay, so then again, kind of skipping to our theory that we need. So we can kind of write this equation out. So a dissociation. So basically we're saying we have our acid, right? So this is our protonated species, acid, and then it's going to dissociate in some amount. So, right, again, not fully dissociated, but some amount of H plus and A minus. And then we can express this as what's called an equilibrium expression. So this is starting to tease where this class is going, because basically once we hit equilibrium, we'll be doing equilibrium of everything. And so now we have our equilibrium expression. So Ka is equal to, so it's generally products over reactants. So H plus concentration over A minus over HA. Okay, so that's just kind of our setup for this. And so now let's get into the math and kind of how this process works. And so now this is our setup for the math of what we're going to be doing. And we're given, and you would normally be given, or you could look up these dissociation constants if you were not provided them. They're pretty standard. But okay, so it tells you it's Ka. So we'll need that. And then we kind of have to go through this little, it's called a ICE table, or I call it a rice table, because, I mean, who doesn't love rice? And so, right, you have your reaction here. Again, your HA dissociating to H and A minus. And then we're trying to figure out what X is, right? So that's the whole point of this exercise, is actually solving for, well, how much was actually disassociated, right? And so kind of, let's again kind of walk through what the problem is saying. So again, we're trying to figure out the pH of a 0.1 molar citric acid solution. But again, right, it's not like our HCl where we could just plug this concentration into here, right? So this is not actually how much H plus is disassociated. And so we have to solve that. Oh, sorry, did you have a question? Rice is just a reaction, and then these are our initial conditions. So it's just showing us, okay, we started with just our acid. Again, when we get into it, right, we might have other things in our initial conditions, but it's just kind of the simple setup. So we have our 0.15 molar of our initial acid, and then this is where the change happens. So this change is, again, the dissociation. So just trying to show this step. So saying, okay, we're going to dissociate some equivalent of X for H plus, some equivalent of X for A minus, and then, of course, right, we'll have to just lose that from this. So that's our change, our reaction. And then, again, kind of what you care about is this equilibrium step. So then this is what we need to plug in. So this is basically what we want to get at, right? So we're saying, okay, some X is going to disassociate. Some of it, of course, will still be there, right? We'll be able to figure it out from our original amount minus X. And so you can kind of see where this is going, right? So we have Ka. We have all these expressions. So we have what H plus is, A minus is, and HA would be. again, after the reaction, after the change. And so, again, kind of where you care about, where it's relevant then for you in your next step is now, so just plug in to our Ka expression. And so I'm just plugging in our Ka for citric acid. So that number, right, I just pulled from the problem is equal to, and I'll rewrite it for a second, so H plus times A minus over HA. And then again, what we're saying is kind of after disassociation. So again, we don't know how much disassociated. We're trying to solve that in X. So now we're given this problem. And so now I'm plugging in the equilibrium expression here. So I'm just plugging in all these, right? X for H, X for A minus, and then this 0.150 minus X for my HA concentration. All right, so then, right, you're here, and this is a good place to be. And so now from here, it's just algebra, which you can kind of tease, again, where this is going. And so now, algebra at this point. And so some people like to plug into fancy calculators. I'll continue going through it. So eventually we'll need the quadratic equation is where this is going. So now I'm just distributing, solving algebra at this point. X squared. So now put everything to one side so I could use a quadratic eventually. So now we're here. Again, if you want to use a fancy calculator, that's fine. I understand that's not necessarily the point of the chemistry class to go through all the math, but rather just get to our answer. But so now I'm just writing the quadratic. And so right, this is our ABC form. So negative b plus or minus the square root of b squared minus 4ac all over 2a. And so now you can just, again, keep plugging it in. I'm just changing my sign for this C here. So then eventually you get somewhere like so, and then of course we only care about the positive value. Now I'll do, oops. So then this should be the one valid answer for x, since again the other one will be negative. So x equals 0.0102. And so again, right now we're saying, okay, now this is my H plus concentration. And so now that we have solved for x, right now we can plug this in to our pH formula. So now we can solve for pH. So we solve for x, which was equal to H plus. So plug in. So again, pH is negative log of the H plus concentration. So then our pH should be about 2 for that one.
So the X is for the hydrogen molecule. When you first substituted, there's the H, then you have the A, and that's how you got the X squared. So how does that? Why is the X equal H, but not the other half of the product?
Well, it equals the concentration of A, right? But then we only care about H plus or X to get the pH. Does that make sense? Because we cared about H plus and A minus, right, with our equilibrium expression. So they're accounted for there, right, saying that, yes, we disassociated to X amount and X amount. So, yeah, it ended up being, right, X squared with the algebra. So, yeah, it was in there. But then when we actually plug in the pH, all we care about is that H plus concentration.
Okay, so it's just, we are only caring about the one product.
Yeah, at the end, because, yeah, again, it's in our expression, so it's in there, but, yeah, we're just trying to solve for x, which is related to that H plus. You just put the negative sign in front of it.
What does the subtracting tell you about the equation? So you said we don't really care about we don't care about subtracting the quadratic formula, but.
Oh, that would just be the unreal answer, right? Like you can't have negative concentration. Yeah. And so again, pH is 1.99. And so you'll just repeat this for write your data. The only thing that's going to change, of course, is the concentration or whatever. So whatever concentration you found for your citric acid molarity, you'll plug that in, do the same math, and then get a pH. Questions about kind of this process, at least? Yeah, so then it's, once you solve for x, remember that x was equal to the H plus, so then, yeah, plugging in that negative log of x. Because that's the definition of pH that you measured by the concentration of H plus ions. So yeah, even though the A minus is the same, it's not. All right, other questions on this one? All right, let's work on some more practice problems for this chapter. So we'll warm up with this one. So we have chlorine trifluoride is used to prepare uranium hexafluoride. And so it's prepared in the following reaction. So 1 equivalent of chlorine gas reacts with 3 equivalents of fluorine to give our 2 equivalents of chlorine trifluoride. And so just see if you can remember what you have to do, right? Just write your equation that relates your rate expressions. So what do we write for this one? How do we express our rate? Maybe try not to overthink it.
Basically, do like a change in y over change in x.
So change in y over change in x, so I like that. And so then what does that mean for chlorine, right? So we can say we have our amount over our change in time. And then is chlorine disappearing or appearing? Appearing, or, because it's on which side so yeah, it's being consumed, so then what should I put in front of it? Negative sign, so right, so now it's decreasing, okay. And then it's equal to, so let's just start putting our rate, so change in fluorine. over change in time. But what do we have to do with fluorine? So it'll also be negative, so it's disappearing. But then how much faster is it disappearing? So 3 times. So then we need to account for that. So 1 over 3. So that rate is equal. Yeah. Yeah, so we're saying, right, for every 1 chlorine that's consumed, there's 3 fluorines, right? But then that means it's being consumed at 3 times the rate, so then you divide it by 3 to get it all the same. And then what about for our chlorine trifluoride here? What do we have to do to it?
1/2, right?
So 1/2, and then positive, and change in chlorine trifluoride over time. Excellent there. So again, just don't forget your coefficients, and don't forget what it means, right, by asking for the rate. So yeah, just a simple expression. All right, let's look at this scenario now. So we're given this process, so CO plus nitrogen dioxide gives us carbon dioxide and nitrogen monoxide. And then we are given the rate law for this reaction. And so, right, just kind of think, what does that rate law mean? And then use that rate law to answer the 2 scenarios. So what happens if we decrease our pressure from NO2? And then what happens if we increase the concentration? So what will the effect on the rate be? So take a few minutes to think about that. So what are we thinking for this one? Maybe even before we start answering. So what is our rate law saying? What does this say here?
It's second order.
So second order with respect to what?
Nitrogen dioxide.
So right, so it's only dependent on our nitrogen dioxide. And then right, second order, so that's probably going to tell us as something doubles, right? The other thing will quadruple. So then what's going to happen if we decrease our pressure from 0.5 ATM to 0.25 ATM. So what factor does this decrease by?
So factor
2 or half? And then, right, we square that. So that means our rate would decrease by 1/4. And then what about B? Any effect from increasing our concentration threefold?
probably a 9-time increase.
But what does our rate law tell us, though?
Constant and NO2 squared. Oh, that's CO.
So then, yeah, if it's CO, what's the answer then? So no effect. And so again, right, CO is not in the rate law expression, so if it had been first order with CO, right, that would have gone up by the same, or 9 if it had been doubled, but yeah, no effect since it's not in our expression, so 0 order with CO.
Are we ever going to see multiple arguments in an expression like NO2 plus CO and like that?
I mean, you could see like K and then NO2CO, right? Or like, because it could have been this, and then that would have said second order with NO2 and first order with CO. So yeah, then this would have had 3 times the effect, right? So the same effect. But yeah, it just depends on the rate law.
So yeah, but that CO in there would be like CO times
Yeah, so then you would look up, so you would see that it goes from 1 to 3, so 3 times as much. So then first order 3 to the 1, so it's still 3, yeah. But again, that's not what we're seeing, so. All right, let's try another one. And so some people believe that supersonic aircraft flights are a concern because of the byproduct of nitric oxide. And so nitric oxide reacts with ozone, and so maybe this could deplete the ozone layer. And so the reaction that people are interested in is shown here. So NO plus ozone gives us our nitrogen dioxide and oxygen. And so now we have to look at what it's telling us. So, okay, it's first order with respect to NO and ozone with a rate constant of 2.20 times 10 to the 7th liters per mole per second. So what is our instantaneous rate of disappearance of NO when these are our initial conditions? So what's it asking? Look at your formula cheat sheet. So what are we thinking for this one?
They're both first order, so final rate law expression will be something like K, NO,
Or rate, yeah, rate is equal to,
BK, NO, and then maybe like CO3.
well, NO, but then, and then O3, right? Is that what you
Yeah.
said?
Was that get a constant as well?
Yeah, because, right, it told you, just like you were saying, right, so it's first order with NO and O3. So yeah, this looks perfect for just setting up, right, your expression. And so that's, I think, the hardest part of the chapter, just, right, again, just kind of figuring out what is it asking. Okay, we set up our problem, and, right, so we're trying to figure out this instantaneous rate. They gave us the rate constant, though, our K, so we can plug that in. And then we're given initial conditions, so it looks like we can just go ahead and plug everything in then. And of course, right, some of these units look funny, but they're just inverse molarity. And so now just plug in. And just plugging in, again, all our initial conditions. Oh, sorry. No. All right, so then do we get something like this for the rate? And so one molarity cancels out, and then still leaving us with 4 points. So I got 2.8 roughly times 10 to the negative fifth. And then that's molarity seconds there. Questions on that one? Okay, let's do some other types of problems. So looking at a little bit of data. And so now we have nitrosyl chloride decomposes to NO and chlorine. So shown there. So determine the rate law, the rate constant, and the overall order for the reaction. So given this data,
Second.
And so again, see if you can figure out your rate constant. So how's this one coming? I think I heard someone say second order. So do we determine that at least? It's kind of like the first step. And so I'd probably just compare, right, data points. So I'm just looking from here to here is times 2. And then what's this difference, though? So times 4. And so what's that looking like for our rate law then? So second order. And so then we can at least start writing our rate expression here. So we have, right, our rate is then equal to whatever our rate constant is times our nitrosyl chloride squared. So that's the first step. And so then once you're here, right, then you can just plug in any data point to determine K. And for the sake of, again, trying to pick the easiest numbers, I'll just pick the first one. So we're given our rate here. So plug that in. So 8 times 10 to the negative 10 is equal to our rate constant times, and then I'll plug in, right, our concentration for this rate here from our data. So 0.1 squared.
So if you chose a different concentration, different rate, you use concentration.
Yeah, but it wouldn't matter. So, right, you could, you could select this one if you like. 7.2 times 10 to the negative 9 is equal to K, 0.3 squared. So either way, your K will agree. So now I'll do the bottom one just for fun. So 7.2 divided by 0.3 squared. Or again, right, if you're good with mental math, you'll realize it's the same thing with the 0.1 squared. And so yes, either way, whatever one you choose, you should get 8 times 10 to the negative 8. And that's inverse molarity, inverse hour for our K, at least I think it's. Questions on this one? All right, so we might be running out of time. So I'll leave a couple of things. So I'll leave this up, this last problem, if people want to work through it either during the break or in recitation. But let's talk about the exam and then the plan for recitation. So your midterm scores were perhaps a little lower than I would like. So they have a distribution. I should have brought the chart, but I didn't really want to risk kind of like exposing people's grades. But basically, well, that was a horrible drawing. But basically, there's very few, like what I would call like genuine A's. So there's yeah, a smaller than a handful of people that scored high. And then there's kind of what I would consider the Bs. And then, right, a large chunk of, again, I'm not assigning grades or anything, but just kind of from the distribution, then a lot of people in the C, and maybe, right, kind of lower range. So that's not quite ideal. The overall average itself was 58 out of 110, which is pretty low. That's like a 52%. I was hoping for a little bit higher on the average. And I think just people aren't devoting enough time to studying, since obviously, right, it's time intensive, but you kind of have to know what formula to use and, you know, how to use your formulas quickly. So I think that is what hurt a lot of people. The multiple choice did not go as well as I thought it would either, so a lot of people lost points there and then didn't really redeem themselves in the free response. So that's kind of where it was. That being said, so I want to offer corrections. So we'll offer, I'll just say 50% back right now. At least that's what I'm thinking. So 50% back for corrections. Again, maybe we could boost this to higher, but we'll kind of see. Because so right now I'm putting into your gradebook just your raw scores, and then later I'll probably do either corrected exams, either with the 50%, or we'll figure out this percentage later. I'm just trying to boost the lower scores higher so that we have a tighter distribution. So yeah, there will be corrections, and so I want to take time to do that today. So today is a good opportunity. So I will open this time for that. So today we can work on corrections. So maybe you can ask your partner, but maybe try to just work by yourself too, right? Just kind of go through your exam, try to go through your formulas, kind of figure out where you might have panicked. And again, right, the point is to kind of figure out too better test taking skills. Some of the multiple choice questions I pulled like from ACS exams. So again, right, I'm like trying to prepare you for standardized testing, where you kind of got to see like what is the problem really asking me for, right? Like what's the trick of this problem? And we can talk about that a little more when you dive into your exams. But the one I was specifically thinking of is like question 9 on the multiple choice. That a lot of people got that one wrong, which I was expecting a lot of people to get it wrong because it was a tricky problem. You have to kind of think about what do I know, what variable do I know, and how can I manipulate that. All right, so I'll stop talking. I'll hand back your exams. You're free to take a break, but probably, don't leave till you have an exam at least. But I would ask that you stay and do work on your test corrections, because most people desperately need test corrections. All right, so yeah, feel free to take your break, and then don't forget about pizza too with the president. So if you want to at least grab pizza, I totally understand.
Is it 50% of the points that you missed?
Yeah, 50% of the points that you missed back. At least that's what I'm thinking right now. Maybe I'll go 75, but let's just start with correcting first.
They're charging us $95 a day to keep you there. And we have to, and the funeral is on March 20th. So, and it's basically $3 grand.
Oh, yeah. So to get points back, like for multiple choice questions, you should, write out some work, some justifications. If it's a math problem, right, that's a little more easy. Just show your work. If it's like another type of conceptual, just write a little explanation of your new answer for credit. And then, did everybody get an exam back? Did I skip anybody? All right, so yeah, again, take your break, do all that, and then, look at your exam, ask me for help on this or anything else. So now's a good time for catch-up.